A function f has derivatives of all orders at x equals 0. Let p sub n of x denote the nth degree Taylor polynomial for f about x equals 0. It is known that f of 0 equals negative 4 and that p sub 1 of 1/2 is negative 3. Show that f prime of 0 is equal to 2. On A, let's show that p sub n of x, well, let's write this out, would be equal to f of 0. You know, if we did it the long way and we were really grinding this out, this would be f of 0 plus f prime of 0 times x plus f second derivative of 0, x squared over 2 factorial, and we could keep going in that pattern. But we're only working with this much right there. Now we know that p sub 1 is negative 3, f of 0 is negative 4, and we're supposed to show that f prime of 0 is equal to 2, but you know, we're plugging 1/2 in for x, so times 1/2. Let's add 4. So we have 1 is equal to f prime of 0 times 1/2, and then multiply both sides by 2, so f prime of 0 must be 2. Letter B, it is known that the second derivative is negative 2/3, the third derivative is 1/3, so find p sub 3 of x. So p sub 3 of x is equal to negative 4 plus 2x minus 2/3 x squared over 2 factorial plus 1/3 x to the third over 3 factorial, which if we simplify is negative 4 plus 2x minus 1/3 x squared plus 1 over 18 x to the third. Letter C, the function h has first derivative given by h prime of x is equal to f of 2x. It is known that h of 0 is equal to 7. Find the third degree Taylor polynomial for h about x equals 0. Now we know that h prime of x is equal to f of 2x. Now we have an approximation for that, and that is we have an approximation for f of x, that's right there. So let's plug 2x in for x. We get negative 4 plus 4x if we plug 2x in for that right there, minus 1/3, actually 4/3, because 2 squared is 4, x squared, and then plus, what would 8 over 18, that's 4/9. So we end up with 4/9 x to the third. Now they want to know what h is. So we're going to integrate and integrate this. So now h of x is equal to, now I think they only want the third degree right there, just the third degree. So we have c minus 4x. I'm taking the antiderivative of this. And then, let's see, what would that be? That's the 4x, and then plus 2x squared, and then minus 4/9 x to the third. So that's the third degree polynomial there. But we know that if we plug 0 in for all of these x's, this piece goes to 0, and then you have 7 equals c. So h of x is 7 minus 4x plus 2x squared minus 4/9 x to the third. The function g has derivatives of all orders, and the Maclaurin series for g is the following. A, use the ratio test and determine the interval convergence of the Maclaurin series for g. So A, we have the limit as n approaches infinity of the absolute value of x to the 2n plus 3 over 2n plus 5. And then times 2n plus 3 over x to the 2n plus 1. So that's equal to the limit as n approaches infinity of the absolute value of 2n plus 3 over 2n plus 5 then there's 2 extra x's on the top. So times x squared. So now the absolute value of x squared has to be less than 1. So -1 is less than x is less than 1. So x has to be between -1 and 1. So there's so far the interval of convergence. Now we have to check our endpoints. So let's check -1. We get n equals 0 to infinity of -1 to the, I'm just going to use, I have a piece of paper with all this on here, n -1 to the 2n plus 1 over 2n plus 3. Now that goes to, let's see, n equals 0 to infinity of 2n plus another n is 3n. So -1 to the 3n plus 1 over 2n plus 3. Well, that does alternate, because if you plug in 0, you get 1. You plug in 1, you get 4. You plug in 2, you get 7. This does alternate. And we can say that the limit as n approaches infinity of 1 over 2n plus 3 is equal to 0, and 1 over 2 times n plus 1 plus 3 is less than 1 over 2n plus 3. So we can say converges by alternating series test. There we go. So we got one endpoint checked. How about the other one? That's n equals 0 to infinity of, it would be -1 to the n, and then 1 to, we'll write it out, 1 to the 2n plus 1 over 2n plus 3. But multiplying by 1 isn't really going to change anything. So this is an alternating series, and we get to the exact same thing we had. So converges by alternating series test. So the interval of convergence is -1 to 1. And we can include the endpoints. Letter B, the Maclaurin series for G evaluated x equals 1/2 is an alternating series whose terms decrease in absolute value to 0, which means, it's an alternating series. The approximation for G of 1/2 using the first 2 non-zero terms of this series is 17 over 120. Show that this approximation differs from G of 1/2 by less than 1 over 200. So letter B, they're saying that they used these two and got a value of 17 over 120. So show that the error is less than 1 over 200. So we're going to use the first omitted term to decide that. So letter B, we can say the absolute value of the error of, let's see, what degree? Of the third degree, is less than or equal to 1/2, because that's what we're plugging in. They said that this is G of 1/2 to the 5th over, I think it was 7, over 7. That's less than or equal to 1 over 32 times 7, because 2 to the 5th is 32. And 7 times 32, that's 4, carry the 1, 224, which is less than 1 over 200. Write the first 3 non-zero terms in the general term of the Maclaurin series for G prime of x. The first, so we want the derivative. And I would normally put that down here, but let's do it. I'm going to erase this. And let's go with G prime of x is equal to 1/3 minus 3/5 x squared plus 5/7 x to the 4th. So it says write the first 3 non-zero. I got that. And the general term. Well, if we started 0, just like they did here, and we did the power rule, multiplied by 2n plus 1, reduce the power by 1, that should get it. Let's see if it does. And then we have a minus ... plus negative 1 to the n. What if we start n with 0? The first one is positive. That works. Then we said this is going to be 2n plus 1, and it's going to be over 2n plus 3. If n is 0, then the first number right here should be 1. Well, 0 plus, oh, I dropped the microphone. Sorry, I dropped the microphone. That's going to be interesting to listen to that. Let me put that back on. There we go. So if we plug 0 in, it should get 1. We do. Plug in 2, we get the, plug in 0. Plug in 1, we get 3. Yeah, that works. And so this should be x to the, if we reduce this by 1, it should just be 2n. And 2 to the 0 is 0. So x to the 0, x to the 2, x to the 4. So that's x to the 2n.